Android architecture. Here is the architectural diagram of Android. Android operating system for cellular telephones and tablet computers. Android began in 2003 as a project of the American technology company Android Incorporation to develop an operating system for digital cameras. In 2004, the project changed to become an operating system for smartphones. Android Incorporation was bought by the American search engine company Google Incorporation in 2005. At Google, the Android team decided to base their project on Linux, an open source operating system for personal computers. Now we are focusing on system apps. System apps function both as apps for users and to provide key capabilities that developers can access from their own app. Android comes with a set of core apps for email, SMS messaging, calendars, internet browsing, contacts, and more. Apps included with the platform have no special status among the apps the user chooses to install. So a third-party app can become the user's default web browser, SMS messenger, or even the default keyboard. Some exceptions apply, such as System Settings app. Here we can see some system apps: Translate, audio effects, etc. Now we are focusing on dialer under system apps. The dialer app is the phone part of your phone system. It is where you place automated outbound calls, and every phone comes with a dialer that does the basic dial numbers and display contacts. Here you can see the dialer in portrait mode, and here you can see an example dialer in landscape mode. Here's example for dialer. Here you can see the activity action intent.action dial. Activity action of action dial is to dial a number as specified by the data. This allows this shows a UI with the number being dialed, allowing the user to explicitly initiate the call. Email. Android comes with native support for email services. Setting up an Android device requires a Gmail account. Setting up Gmail activates other email dependent components on Android devices. Some email dependent features include security and recovery mechanisms. Another email dependent feature is access to the Play Store, a marketplace for Android applications. Here you can see email app. Here is an example code. Here you can see intent.action send and set data type, and other put extras like extra intent.extra email, intent.extra cc likewise. Here you can see intent.action send. Active action of action send is to deliver some data to someone else. Who the data is being delivered to is not specified. It is up to the receiver of this action to ask the user where the data should be sent. Now we are focusing on calendar. Google Calendar is the stock calendar app for Android users. Some users may have to download the actual Google Calendar app, but even the default app syncs with your Google Calendar seamlessly. You can see here Google app, Google Calendar app here. Here you can see example code for calendar view. Calendar view is a calendar widget for displaying and selecting dates. The range of dates supported by this calendar is configurable. Here's an exception example. Illegal argument exception. For example, this can happen in setDateLong method in class calendar view when of the provided date is before the minimal or after the maximal date. Now we are focusing on camera. The camera app is typically found on the home screen, often in the favorites tray. This is Android camera architecture. Here we can get you can see raw buyer input. It go through statics generation and 3A algorithms, and then camera section, and it has flash, lens and sensor. Here you can see image processing section. You can see the flow here: hot pixel correction, demosaic, noise reduction, shading correction, then geometric correction, then color correction, then tone curve adjustment, then edge enhancement. Then it goes through scale and crop, and YUV output 1, and again scale and crop, YUV output 2, scale and crop, YU output 3, and scale and crop, JPEG encoder, JPEG output, and all these outputs goes to request control. Here also you can see scale and crop, raw bare output, and request control, and it provides the output as metadata and image streams. Here you can see the sample code. We are focusing on android.provider.mediastore.action image capture. Action image capture is standard intent action that can be sent to have a camera application capture an image and return it. As a exception example, here security we can see security exception. If your app targets M and above and declares as using the manifest.permission.camera permission, which is not granted, then attempting to use this action will result in a security exception. Here Android by default comes with a set of applications that make Android devices usable from the offset. In this architectural diagram you can see many apps: home, calendar, contacts, music, camera, gallery, SMS, phone, alarm clock, time, email. Likewise, as an example, you can see here usage of SMS manager and the send text method. SMS manager manages SMS operations such as sending data, text and PDU SMS messages. Get this object by calling the static method getDefault. To create an instance of SMS manager associated with the specific subscription of ID, call getSMS manager for subscription ID int. This is typically used for devices that support multiple active subscriptions at once. As an exception example, we can consider illegal argument exception. If the destination address or text are empty in send text message, this exception will be thrown. Now we are focusing on Java API framework. The entire feature set of the Android OS is available to you through APIs written in Java language. These APIs form the building blocks you need to create Android apps by simplifying the reuse of core modular system components and services. Here in this diagram you can see this one, the Java API framework, just below system maps. As an example, we can take Android package. This package contains resource classes used by applications included in the platform and defines application permissions for system features. Now we are considering content providers under Java API framework. A content provider manages access to a central repository of data. A provider is part of an Android application which often provides its own UI for working with the data. However, content providers are primarily intended to be used by other applications which access the provider using a provider client object. Together, providers and provider clients offer a consistent standard interface to data that also handles interprocess communication and other secure data access. Here you can see a relationship between content provider and other components. Here sharing access to your application data with other applications, sending data to a widget, and returning custom search suggestions for your application to the search framework using search recent suggestions provider. synchronize an application data with your server using an implementation of abstract threaded sync adapter, loading data in your UI using cursor loader, and here you can see data storage and another data storage. As an example, we can consider content provider class. Content providers are one of the primary building blocks of Android applications, providing content to applications. They encapsulate data and provide it to applications through the single content resolver interface. A content provider is only required if you need to share data between multiple applications. For example, the contacts data is used by multiple applications and must be stored in a content provider. If you don't need to share data amongst multiple applications, you can use a database directly via SQLite database. As an error example, data access methods such as insert URI content values and update URI content values bundle may be called from many threads at once and must be thread safe. Other methods such as onCreate are only called from the application main thread and must avoid performing lengthy operations. This is more like a guideline. Now we are considering view system. Can use to build an app's UI including lists, grids, text boxes, buttons, and even an embeddable web browser. Here you can see Android view system. You can see activity here, font, window, decorator view, title bar, and in the under decorator view you can see title bar and content, and under content you can see view groups, and you can get another view group under one view group, and under that you can get views, view, and under this view group also you can get view and view also, and this can lead to other things. As an example, we can take web view. In most cases we recommend using a standard web browser like Chrome to deliver content to the user. Web view objects allow you to display web content as part of your activity layout, but lack some of the features of fully developed browsers. A web view is useful when you need increased control over the UI and advanced configuration options that will allow you to embed web pages in a specially designed environment for your app. As an exception example, you can take illegal state exception. If WebView has already been initialized in the current process in disable WebView method in class WebView. Now we are focusing on managers. Managers for activity, location, package, notification, resource, telephony, and window. In this diagram you can see managers also. Now we are focusing on activity manager. It manages the life cycle of apps and provides a common navigation backstack. In this diagram you can see important state path of an activity. The square rectangles represent callback methods you can implement to perform operation when the activity moves between status. Colored ovals are major states the activity can be in. There are three key loops you may be interested in monitoring within your activity. The entire lifetime of an activity happens between the first call to create bundle on create bundle through a single final call to on destroy. And an activity will do all setup of global state in on create and release all remaining resources on destroy. For example, if it has a thread running in the background to download data from the network, it may create the thread in on create and then stop the thread on destroy. The visible lifetime of an activity happens between a call to on start until a corresponding call to on stop. During this time, the user can see activity on screen, though it may not be in the foreground and interacting with the user. Between these two methods, you can maintain resources that are needed to show the activity to the user. For example, you can register a broadcast receiver on in onStart to monitor for changes that impact your UI and unregister it in onStop when the user no longer sees what you are displaying. OnStart and onStop methods can be called multiple times as an activity becomes visible and hidden to the user. The foreground lifetime of an activity happens between a call to on resume until the corresponding call to on pause. During this time, the activity is invisible, active and interacting with the user. An activity can frequently go between resumed and paused states. For example, when a device goes to sleep, when the activity result is delivered, when a new intent is delivered. So the code in these methods should be fairly lightweight. Here you can see activity launch state, and here then I go to on create. It's called when the activity is first created. This is where you should do all your normal static setup, create views, bind data to list, etc. This method also provide you with a bundle containing activities previously frozen state, if there was one, always followed by on start. So we move to on start. It's called when the activity is becoming visible to the user, followed by on resume if the activity comes to the foreground, or on stop if it is become hidden. Then we can go to on resume. It's called when the activity will start interacting with the user. At this point, your activity is at the top of its activity stack with user input going to it, always followed by on pause. So here we can have now activity running state. Another activity comes to onto the background then, and then it go to on pause. It's called when the activity loses foreground state and is visible. It's called when the activity loses foreground state is no longer focusable or before transition to stopped, hidden or destroyed state. The activity is still visible to the user, so it's recommended to keep it visually active and continue updating the UI. Implementation of this method must be very quick because the next activity will not be resumed until this method returns, followed by either on resume if the activity returns back to the front, or on stop if that becomes visible to the user. So you can see here if user returns to the activity, then we can call move back to on resume, or this is also killable. So it can move to app kill, the app process killed state also. Then it can move to on stop. The activity is no longer visible. On stop method. It's called when the activity is no longer visible to the user. This may happen either because new activity is being started on top, an existing one is being both in front of this one, or this one is being destroyed. This is typically used to stop animations and refreshing the UI, etc. Followed by either restart if this activity is coming back to interact with the user, or on destroy if this activity is going away. So if user navigate to the activity, then it goes back to the on start, or so this this method is killable, so it can go out to app process killed state also. The activity is finished or being destroyed by the system, then we move to on destroy method. The final call you receive before your activity is destroyed. This can happen either because the activity is finishing, someone called activity finish on it, or because the system is temporarily destroying this instance of the activity to save space. You can distinguish between these two scenarios with is finishing method. And then it moved to activity shutdown state. Here I can especially mention after calling in on stop or on pause method, those methods are killable. So apps with higher priority need memory, and it will go to app process killed state. Then user navigate to the activity and can move back to on create. As an example, we can take activity. An activity is a single focused thing that user can do. Almost all activities interact with the user, so the activity class takes care of creating a window for you in which you can place your UI with set content view method. While activities are often presented to the user as full screen windows, they can also be used in other ways as floating windows via a theme with r.attr.window is floating set, multi-window mode, or embedded into other windows. There are two methods almost all subclasses of activity will implement: on create bundle and on pause. As an exception example, we can consider activity not found exception. Method start activity indent bundle in activity class throws activity not found exception if there was no activity found to run the given intent. Now we are considering location manager. Location services are used for location management. GPS or cell tower are used to get location of device. Here you can see state of platform APIs with location manager. Location manager is an Android framework class. It provides access to the system location services. It can get the location from GPS, network, and Wi-Fi. But at a given time, it can get the location from only one provider. In this diagram, you can see hardware section. Sensors are there, and sensor HAL, and then sensor manager, and this is platform layer, and it go through the apps. So here GPS and GPS HL and GPS location provider, and can go through location manager and to apps. And here GPS location provider can also connect network location provider NLP, and here Wi-Fi VPA sub and CFG 802211, and it go through network location provider, and location manager can access NLP, and it go through the apps. And here you can see cell and RIL, and it can access network location provider NLP, and it's go through location manager can access NLP, and it's go through the apps. And location manager can also provide a geofence and passive LP. As an example, we can consider location manager. There's a code segment for location manager, and location manager provide access to the system location services. These services allow applications to obtain periodic updates of the device's geographical location, or to be notified when the device enters the proximity of a given geographical location. As an exception example, we can consider illegal argument exception. If provider is null in this exception can throw if the provider is null in is provider enabled string method in location manager class. Now we are considering package manager. Package manager keeps track of all packages available in a system and service those packages can provide. Android uses a special extension for packages called APK, Android package. Here you can see APK installation process. Here URI to package installer, then package installer activity, then let's go to install app progress. Here install package process, it has following steps: waiting, add the package to the queue for the installation process, determine the appropriate location of the packaged installation, determine installation, install update new, a copy of the APK file to the given directory, determine the UID of the app, request to install daemon process, request to install the daemon process, create the application directory and set permissions, exclusion of DEX code to the cache directory, to reflect and packages dot list system data packages dot XML the latest status, broadcast to the system along with the name of the effect of the installation is complete package, intent.action package added. If the new intent.action package replaced, then the case of an update. So this connect to the app dir OB server is there, package manager service is there here, and this also communicate with installer.com android dot installer com.android.server.pm. this connect to the dev socket install d, and here this one is connected to the package manager, and then it install app progress is finished. Here this package manager is within system server UID equals system, and under that activity manager is there, account manager there, and other things are there. This is under zygote UID equal root, and this is it's under init.rc, and install the service UID equal root is under that, and it's going to the /div/socket /install d. As an example, we can take package manager in this sample code. Reference to Android package manager. Package manager is class for retrieving various kinds of information related to the application packages that are currently installed on the device. As an exception example, package manager.name not found exception. This exception is thrown when a given package, application or component name cannot be found. Notification manager enables all apps to display custom alerts in the system in the status bar. Here you can see a notification anatomy. This is a notification with basic details. The design of a notification is determined by system templates. Your app simply defines the contents for each portion of the template. Some details of the notification appear only in the expand view. Here the most common parts of a notification are indicated here. Small icon, this is required, and set with set small icon method. App name, this is provided by the system. Timestamp, this is provided by the system, but you can override with set when or hide it with set show when false method. Basically calling set show when false as a parameter. And large icon, this is optional, usually used only for contact photos. Do not use it for your app icon, and set with set large icon method. And title, this is optional and set with set content title method. Text, this is optional and set with set content text method. We strongly recommend using system templates to ensure proper design compatibility on all devices. If necessary, however, you can create a custom notification layout. This is example code here. We can consider notification manager here. This is a notify method also, and notification manager is class to notify the user of events that happen. This is how you tell the user that something has happened in the background. Notifications can take different forms. A persistent icon that goes in the status bar and is accessible through the launcher when the user selects it. A designated intent can be launched. And turning on or flashing LEDs on the device, or alerting the user by flashing the backlight, playing a sound, or vibrating. As an exception example, we can consider security exception. It throws a security exception if policy access is not granted in this package. For example, this can be thrown in add automatic send rule method in notification manager class. Now we are considering resource manager. It's providing access to non-code resources such as localized strings, graphics, and layout files. Here you can see two different devices, each using different layout resources. Almost every app should provide alternative resources to support specific device configurations. For instance, you should include alternative drawable resources for different screen densities and alternative string resources for different languages. At runtime, Android detects the current device configuration and loads the appropriate resources on your app. As an example, we can consider this code segment. Here, first line of the code make use of r.id.myImageView to get image view defined with id myImageView in a layout file. In the second line of the code makes use r.drawable.myimage to get an image with the name myimage available in drawable subdirectory under /res. As an error example or as an exception example, we can take illegal state exception. When overriding onMeasure int method in ImageView class, you must call setMeasure dimension int to store the measured width and height of this view. Failure to do so will trigger an illegal state exception thrown by measure int. Calling the superclass onMeasure int is a valid use. Now we are considering telephony manager. All activities related to making phone calls and sending text messages are handled by telephony service. It makes possible to make calls and receiving text messages. Here you can see architecture of Android telephony. Android telephony architecture works in 4 layers here. These 4 layers are communication processor, radio interface layer, RIL, framework services, and applications. Communication processor, it is an input-output processor to distribute and collect data from a number of remote terminals. It is specialized processor designed to communicate with data communication network. Radio interface layer, it is a bridge between the hardware and Android phone framework services. Rather, we say it is a protocol stack for telephone. It has 2 main components that are RIL daemon. It starts when the Android system starts. It reads the system properties to find a library that is to be used for vendor RIL. The other component is vendor RIL. It is also known as RIL driver. It can be understood as a library that is specific to each modem. Framework services. Telephony framework starts and initializes along with the system. All the queries by application API are directed to RIL using these services. Application. These are the application UI related to telephony, such as dialer, SMS, MMS, call tracker, etc. These applications start with the Android system boot up. These are tied with framework services of telephony. This is Android telephony framework. Here in application you can see a phone, third-party telephony app. In the framework you can see telephony manager and internal telephony package. This is generally used for default telephony app.apk. You can see libraries, runtime, Java, VM and libraries, and RIL daemon. In the Linux kernel you can see RIL driver, and communication processor you can see cellular protocol stack. As an example, we can consider telephony manager in this code segment. It provides access to information about the telephony services on the device. Applications can use the methods in this class to determine telephony services and states, as well as to access some types of subscriber information. Applications can also register a listener to receive notification of telephony state changes. As an exception example, we can consider illegal argument exception. When the slot index is invalid in get network country ISO int in telephony manager class. Now we are considering window manager. With acquisition of Surface Flinger, window manager draw different windows on screen for interaction. Surface Flinger manages all the output on the screen. Here you can see an app window on different devices. So one device, and this is in another device, and this is in another device with app windows. As an example, we can consider window manager in this code segment. Window manager is the interface that apps use to talk to the window manager. As an exception example, we can consider window manager.bad token exception. Exception that is thrown when trying to add view whose layout params token is invalid. Now we are considering native C++ libraries. Many core Android system components and services such as ART and HAL are built from native code that require native libraries written in C and C++. The Android platform provides Java frameworks APIs to expose the functionality of some of these native libraries to apps. For example, you can access OpenGL ES through the Android framework's Java OpenGL API to add support for drawing and manipulating 2D and 3D graphics in your app. Here you can see libraries here in this diagram after Java API framework and on top of HAL here, and this is libraries in this part. As an example, we can consider OpenGL ES. Now we are considering WebKit in native C and C++ libraries. WebKit is a browser engine developed by Apple and primarily used in its Safari web browser as well as all iOS web browsers. It can also process annotations in Java. WebKit is also used by the BlackBerry browser, PlayStation consoles beginning from the PS3, the Tizen mobile operating systems, and a browser included with Amazon Kindle ebook reader. WebKit's C++ application programming interface API provides a set of classes to display web content in Windows and implements browser features such as following links when clicked by the user, managing a back forward list, and managing a history of pages recently visited, files and classes. Here you can see a WebKit architecture. This is the application, and WebKit thing layer to link against from the applications. WebCore rendering layout, network access, multimedia, accessibility support, etc. And JS engine, the JavaScript engine, JavaScript core by default, platform specific hooks to implement generic algorithms. As an example, we can consider Android.WebKit. It provides tools for browsing the web. As another example, we can consider safe browsing response, used to indicate an exact action to take when hitting a malicious URL. Instances of this class are created by the web view and passed to webview client dot onSafe browsing hit webview web resource request int safe browsing response. The host application must call show interstitial boolean, proceed boolean, or back to safety boolean to set the web view's response to the safe browsing hit. Now we are considering OpenMAX AL. OpenMAX AL is the interface between multimedia applications such as a media player and the platform media framework. It allows companies that develop applications to easily migrate their applications to different platforms. Customers that support OpenMAX AL application programming interface (API). Here, OpenMAX layers can be implemented together or independently from the other layers. This is application, this is OpenMAX AL. Media applications can be written portably independent of underlying media platform. Here application layer define high level playback when recording API media platform media frameworks here. And this is OpenMAX IL. Integration layer defines media component interfaces. Media components can be integrated into flexible media graphs for advanced streaming media processing. Here you can see audio component like for example MP3 video component, for example H.264 image component JPEG, for example. And OpenMAX DL development layer defined low-level media primitives and concurrency construct. Media components can be written using primitives for portability across diverse parallel and silicon architecture. Here you can see a media engine, CPUs, DSP, hardware accelerators, etc. Here in OpenMAX AL, this is the location we are in this layered diagram. This is OpenMAX AL. As an example, we can consider OpenMAX /OpenMAX al.h header file. This file is the standard OpenMAX AL header file. In this code segment, the engine object is the entry point to the OpenMAX AL API. This object enables you to create all other objects used in OpenMAX AL. As an error example, we can consider XA result resource error. Operation failed due to a lack of resources, usually a result of object realization. Now we are considering Libc. LLVM's Libc++ is the C++ standard library that has been used by the Android OS since Lollipop, and as of NDK R18 is the only STL available in NDK. Here you can see the LLVM logo, a serialized Y1. As an example, we can consider Libc++ shared.so library. The shared library for Libc++ is Libc++ shared.so, and the static library is Libc++_static.a library. As another example, we can consider this situation. Libc++ is not a system library, so if you use Libc++_shared.so, it must be included in your app. If you are building your application with Gradle, this is handled automatically. This is more like a guideline. Now we are considering media framework. Media framework provides recording and playback of numerous audio, video and picture formats including MPEG-4, MP3, AME, H.264, AAC, PNG and JPG. Android includes Stagefright, a media playback engine at the native level that has built-in software-based codecs for popular media formats. This is media architecture here. Media applications interact with Android native multimedia framework according to the following architecture. Application framework. At the application framework level, level is an application code that utilizes Android.media APIs to interact with multimedia hardware. Binder IPC. Binder IPC proxies facilitate communication over process boundaries. They are located in the framework /AV/media /LIB media directory and begin with the letter L. Actually letter I. Native multimedia framework. At the native level, Android provides a multimedia framework that utilizes Stagefright engine for audio and video recording, playback. Stagefright comes with the default list of supported software codecs, and you can implement your own hardware codec by using the OpenMAX integration layer standard. For more implementation details, see the media player and Stagefright component located in frameworks /AV/media. OpenMAX integration layer. The OpenMAX IL provides a standardized way for Stagefright to recognize and use custom hardware-based multimedia codecs called components. You must provide OpenMAX plugin in the form of a shared library name libstagefright w.so. This plugin links Stagefright with your custom codec components, which must be implemented according to the OpenMAX IL component standard. Here under application framework you can see media codecs and Android.media classes and Android.media, and in binder IPC proxies you can see frameworks /AV /libmedia and media player binder is connect to media player service.cpp here in native framework. In native frameworks /AV, media player service is here, and media player /media /libmedia player service here, and media player service.cpp here, and here OpenMAX integration, OpenMAX IL components here, hardware codec implementation of OpenMAX plugin here, libstagefright w.so here, and Stagefright engine is here, frameworks /AV /libstagefright here, media source.cpp, and OpenMAX core is here under Stagefright engine. As an example, we can consider local underscore module libs module colon equal libstagefright W. Build your plugin as a shared library with the name libstage w.so in your product make file. As another example, we can consider Android_media player_start function here. The source file of this code is Android_media player.cpp. As an exception example, we can consider illegal state exception. It is called when an invalid state in a method start in media player class. Actually, that error is propagated through Android media and Android_media player_start method in start function in Android_media player CPP code. That's the path going through going for the illegal state exception. Now we are considering OpenGL ES. Android includes support for high performance 2D and 3D graphics with the Open Graphics Library OpenGL, specifically the OpenGL ES API. OpenGL is a cross-platform graphics API that specifies the standard software interface for 3D graphics processing hardware. OpenGL ES is a flavor of the OpenGL specification intended for embedded devices. EGL works on top of the native windowing system such as WGL Windows, GLX or X Windows Linux or Mac OS XS Quartz. With EGL specifications, cross-platform development becomes easier. Here you can see a programmable pipeline architecture OpenGL ES 3.0. OpenGL ES API is here. It's move to transform feedback, and here also input is here, and it's moved to vertex shader primitive assembly, and it's also connect to transform feedback, and this is a flip where, and this also this move to this section with vertex info, and here clip viewport calling is here, and it's moved to rasterization, and it's moved to fragment shader primitive assembly, and it moved to here fragment shader performs section, and fragment shader moved to per fragment operations, and then output frame buffer to this section. Here V1, V2, V3 is moving to V1, V2, V3 here. This is color info, and it's moving into vertex info and provided to this section, and vertex shader is moving to vertex shader program performs coordinate transformation, pre-vertex lightning calculation, data processing for fragment shader. Here fragment shader move to fragment shader performs pre-fragment color calculation, interpolation of color per fragment, discard any unwanted fragments. Here output frame buffer move to under user control, under system control, and operation description. These are moving into EGL layer and to the display. Here as an example you can see GL draw arrays. GL draw arrays specify multiple geometric primitives with very few subrouting calls. Instead of calling a GL procedure to pass each individual vertex, normal, texture coordinate, edge flag or color, you can specify separate arrays of vertices, normals and color and use them to construct a sequence of primitives with a single call to GL draw arrays. Here you can see a GL ES 20.gl draw arrays function. As an error example, we can consider GL underscore invalid underscore enum. GL underscore invalid underscore enum is generated if the mod is not an acceptable value in function GL draw arrays, GL enum, GL int and GL size I. And here there are other native C and C++ libraries. As an example, we can consider LIBM. There is a separate LIBM for math functions following the usual Unix tradition, but like LIBC, this is automatically linked by the built systems. Now we are considering Andriod Runtime. For devices running Android version 5.5, API level 25 or higher, each app runs in its own process and with its own instance of the Andriod Runtime ART. ART is written to run multiple virtual machines on low memory devices by executing DEX files, a bytecode format designed especially for Android that's optimized for minimal memory footprint. Build tools such as D8 compile Java sources into DEX bytecode, which can run on the Android platform. Here you can see Andriod Runtime here in this section, in this diagram. Now we are moving into Andriod Runtime ART. Andriod Runtime ART is the managed runtime used by applications and some system services on Android. ART and its predecessor Dalvik were originally created specifically for the Android project. ART as the runtime executes the Dalvik executable format and DEX bytecode application. DEX bytecode specification. Here you can see a comparison of Dalvik and ART architecture. Here resource and native code is going here, and source here, and DEX file is here, and it's moving into zip and APK. Then installation is going here, install, and DEX file is here. In Dalvik it's DEX opt here, and ODEX file is here. Quick and DEX is there, and is moved to Dalvik and native, and libraries are linked from here, and there's a just-in-time process. And with Andriod Runtime ART, ELF file is here, and DEX to OOT is there, and DEX and native code is there here also, and it's moving to ART and native, and libraries are connected here. As an example, we can consider product underscore copy underscore files plus equal file name colon system /etc payloaded stroke classes. Example usage in products device.mk. The preloaded classes list is a list of classes the Zygote initializes on startup. This saves each app from having to run these class initializers separately, allowing them to start up faster and share pages in memory. The preloaded classes list file is located at frameworks /base /config /preloaded classes by default, and it contains a list that's tuned for typical phone use. This might be different for other devices such as wearables and must be tuned accordingly. Be careful when tuning this. Adding too many classes wastes memory when unused classes get loaded. Adding too few classes forces each app to have its own copy, which again wastes memory. As an exception example, java.lang.nullPoint exception attempt to write to field int android accessibility service info.flags on a null object reference. ART gives you as much context and details as possible when runtime exceptions occur. ART provides expanded exception details for java.lang.classCast exception, java.lang.classNotFound exception, and java.lang.nullPoint exception. Later versions of Dalvik provided expanded exception detail for java.lang.array index out of bounds exception and java.lang.array_store exception, which now include the size of the array and the out of bound offset, and ART does this as well. Now we are moving into core libraries. The Android core libraries fall into three main categories: Dalvik VM specific library, Java interoperability libraries, Android libraries. This is kind of bit older description with related to Dalvik VM. And here in this diagram under ART in Android Runtime, with related to Android Runtime, these libraries are there. As an example, we can consider Android.app. It contains high-level classes encapsulating the overall Android application model. As an exception example, authentication required exception. Specialization of security exception that is thrown when authentication is needed from the end user before viewing the content. Now we are considering hardware abstraction layer. The hardware abstraction layer provides standard interfaces that expose device hardware capabilities to the higher level Java API framework. The HAL consists of multiple library modules, each of which implements an interface for a specific type of hardware component, such as the camera or Bluetooth module. When a framework API makes a call to access device hardware, the Android system loads the library module for that hardware component. Here you can see hardware abstraction layer and .HL components: audio, automotive, Bluetooth, camera, DRM, graphics, input, media, peripherals, sensors, storage, TV. As an example, we can see a HL interface definition language here. HL interface definition language, or HIDL, pronounced HIDL, is an interface description language, IDL, to specify the interface between HAL and its users. It allows specifying types and method calls collected into interfaces and packages. More broadly, HIDL is a system for communicating between code bases that may be compiled independently. As of Android 10, HIDL is deprecated and Android is migrating to use AIDL everywhere. This is an example of HIDL C++ as a HAL for a HAL client. Android O re-architects the Android OS to define clear interfaces between the device-independent Android platform and device and vendor-specific code. Android already defines many such interfaces in the form of HAL interfaces defined as C headers in hardware/lib hardware. HIDL replaces these HAL interfaces with stable versioned interfaces which can be client and server-side HIDL interfaces in C++ or Java. This is another example for different example for HIDL Java code. In Android 8.0, the Android OS was re-architected to define clear interfaces between the device-independent Android platform and device and vendor-specific code. Android already defined many such interfaces in the form of HAL interfaces such as C headers in hardware/lib hardware. HIDL replaced these HAL interfaces with stable versioned interfaces which can either be in Java or be client and server-side HIDL interfaces in C++. Now we are considering audio. Android's audio hardware abstraction layer HAL connects the higher level audio specific framework APIs in Android.media to the underlying audio drivers and hardware. The audio HAL defines the standard interface that audio services call into. It must be implemented for the audio hardware to function correctly. The audio HAL interface is defined using HIDL and in .hal files and XSD schemas for configuration files shown as follows. The audio HAL interface. These commands and audio data is going to move to HIDL and audio HAL, and configuration parser is accessible through XSD to XML files. This is the system here, and audio policy in configuration files, audio policy and audio effects XML configuration files are considered to be the part of the audio HAL interface. These files must conform to their schemas, and the conformance is verified by VTS test. In audio HAL API, the audio HAL contains following APIs: core HAL and effect HAL and common HAL. In core HAL, the core HAL is the main API used by Audio Flinger to play audio and control audio routing. And effect HAL, the effect HAL API is used by the effect frameworks to control audio effect. You can configure pre-processing effects such as automatic gain control and noise suppression through the effects HAL API. Common HAL, the common HAL is a library of common data types used by the core and effect HAL APIs. it has no interfaces and no associated VTS test, as it only defines data structure, the data structures. Here you can see Android audio architecture. This is application framework. At the application framework level is the app code, which utilizes the Android.media APIs to interact with the audio hardware. Internally, this code calls corresponding JNI glue classes to access the native code that interacts with the audio hardware. So on JNI, this JNI code associated with Android.media is located in the frameworks /base /core/JNI and frameworks /base /media /JNI directories. This code calls the lower level native code to obtain access to the audio hardware. And here we go to media framework. Sorry, this is a native framework. The native framework is defined in frameworks /AV /media /lib media, and provides a native equivalent to the Android.media package. The native framework calls the binder IPC proxies to obtain access to audio specific services of the media server. Binder IPC. The binder IPC proxies facilitate communication over process boundaries. They are located in the frameworks /AV /media /lib media directory and begin with the letter I. Media server. The audio services in the media server located in frameworks /AV /services /audio flinger is the actual code that interact with your HAL implementation. HAL. The HAL defines the standard interface that audio services call into and that you must implement to have your audio hardware function correctly. The audio HAL or audio HAL interfaces are located in hardware /lib hardware /include hardware. See hardware /audio.h for additional details. And kernel driver. The audio driver interacts with the hardware and your implementation of the HAL. You can choose to use ALSA, OSS, or a custom driver of your own at this level. The HAL driver agnostic. Note, if you do choose ALSA, we recommend using external /tiny tiny ALSA for the user portion of the driver because of its compatible licensing. The standard user mod library is GPL licensed. Here you can see the application framework. It includes a media player app, media recorder app, Android.media **, and JNI. Here we can see Android_media_ number of files with .cpp. Native framework, you can see audio recorder.cpp, audio track.cpp, and other non-binder sources. In binder IPC proxies, you can see I audio recorder.cpc, I audio track.cpc, I audio flinger.cpc, and other I binder name cpp class files. In media server, you can see this and audio policy service. It's can interact with audio flinger service, and that move into HAL and in here you can see audio HAL implementation, and in kernel you can see ALSA or OSS or custom driver. Here the application frameworks, here JNI is moving to native framework, and it's moving to bind IPC proxies. It's moving to audio flinger, which interact with audio policy service, and audio flinger, then this audio flinger service moving to HAL, and HAL is connected with the kernel. As an example, we can consider audio.h file. It's a header file. And as another example, we can consider audio underscore hv underscore device underscore open module ampersand device function. This is a convenience API for opening and closing a supported device. As an error example, you can get the output of the audio, return value of the audio underscore hv underscore device underscore open module ampersand device function, and if it is value is greater than 0, it's an error here, and here you can see that the error handling code is here. Now we are considering Bluetooth. Heidel defines the interface between Bluetooth stack and the vendor implementation. To generate the Bluetooth Heidel files, pass the Bluetooth interface files into the Heidel generation tool. The interface files are located in hardware/interfaces/Bluetooth. Android Bluetooth architecture. A Bluetooth application communicates with the Bluetooth process through binder. The Bluetooth process uses JNI to communicate with the Bluetooth stack and provide developers with access to various Bluetooth profiles. This diagram shows the general structure of Bluetooth stack, and this is the Bluetooth architecture here. Application framework. At the application framework level is the application code, which uses Android.Bluetooth APIs to interact with Bluetooth hardware. Internally, this code calls the Bluetooth process through the binder IPC mechanism. Bluetooth system service. The Bluetooth system service is located in packages/apps/Bluetooth. Is the package as an Android app and implements Bluetooth services and profiles at the Android framework layer. This app calls into native Bluetooth stack via JNI. And JNI code, the JNI code associated with Android.Bluetooth is located in packages/apps/Bluetooth/JNI. The JNI code calls into the Bluetooth stack when the certain Bluetooth operations occur, such as when devices are discovered. Bluetooth stack. The default Bluetooth stack is provided in AOSP and is located in /system/BT. The stack implements the generic Bluetooth HAL and customizes it with the extension and configuration changes. vendor implementations. Vendor devices interact with the Bluetooth stack using hardware interface design language HIDEL, and HIDEL defines the interface between the Bluetooth stack and vendor implementation. To generate the Bluetooth HIDEL files, pass the Bluetooth interface files into the HIDEL generation tool. The interface files are located in hardware/interfaces/Bluetooth. And here you can see application framework. Under that we can here see apps and Bluetooth, Android.Bluetooth, and in Bluetooth process we can see Bluetooth service and Bluetooth profiles. In there now is JNI is there, and below that Bluetooth stack is there, and Bluetooth app layer is here, Bluetooth embedded system is here, and it's connected with the HIDEL, and HIDEL interfaces are here, and it's connect with the vendor implementation. Their Bluetooth control is here. As an example, we can consider Bluetooth.h file. This is a header file. As another example, we can consider enable function. Enables Bluetooth a single Java source code. This is the function definition. This is the function kind of a declaration. As another example, we can consider bt underscore status underscore fail. This is a Bluetooth error status. The operation, it means the operation has failed. Now we are moving into camera. HIDEL defines the interface between Bluetooth stack. Now we are moving into camera. Android's camera hardware abstraction layer HAL connects the higher level camera framework APIs in Camera 2 to your underlying camera driver and hardware. The camera subsystem includes implementation for camera pipeline components, while the camera HAL provides interfaces for use in implementing your version of these components. Here you can see a camera architecture. Here you can see this blue color Java classes, and binder interfaces are in red color, and green C++ classes and HIDEL interfaces are here in orange color. And this is camera API version 2, camera service, and binderized HAL. And in app framework, at the app framework level is the apps code, which uses camera 2 API to interact with camera hardware. Internally, this code calls corresponding binder interfaces to access native code that interact with the camera. AIDL, the binder interfaces associated with camera service, can be found at frameworks /AV/camera /AIDL/Android/hardware. The generated code calls the lower level native code to obtain access to the physical camera and returns the data that is used to create camera device and eventually camera capture session. Objects at the framework level, and native framework. This framework residing in frameworks /AV/ provide a native equivalent to the camera device, and camera capture session classes. Also see NDK camera 2 reference. Bind IPC interface. The bind IP interface facilitates communication over process boundaries. There are several camera binder classes located in frameworks /AV/camera/AIDL/Android hardware directly that call into camera service. iCamera service is the interface to the camera service, and iCamera device user is the interface to a specific open camera device, and an iCamera service listener here, and this is iCamera's device user, which is the interface to a specific open camera device. An iCamera service listener and iCamera device callbacks are the respective camera service and camera device callbacks to the application framework. And iCamera service is the interface to the camera service. And the camera service is located at frameworks/AV/services/camera/libcamera service/camera service.cpp is the actual code that interact with HAL. HAL, the hardware abstraction layer, defines the standard interface that the camera service calls into and that you must implement to have your camera hardware function correctly. And this is camera cooperation model. In the capture request, there are per frame settings, target surface, and target another target surface, and this capture. Then camera device is there, pending request queue is here, and multiple requests are here, and in the queue is moved to camera hardware. In-flight capture queue is here, and multiple requests are here, and is connect to output image queries are here, and it's configured output is moved to configured output surfaces. There are multiple surfaces are here. In in-flight capture queue, it's moved to go through on capture complete function, and then it's moved to capture result setting. In the capture result settings used by hardware status and original capture request is here, and this is the camera hardware, and this is the lens here. As an example, we can consider camera 3 header camera 3.h, and it's a header file. And as another example, we can consider camera 3 underscore buffer underscore request underscore status underscore t, and strict request underscore stream underscore buffer. It's a pointer. This function. And as an error example, we can consider camera 3 underscore msg underscore error. An error has occurred. Camera 3 underscore notify underscore message dot error contains the error information. It's in the enum camera 3 underscore msg underscore type. And we are considering now sensors. It's a hull. There are hull services. So here, how to create your own Android service. to manage a dedicated hardware resource. This is a service in AIDL. In order to interact with your hardware from the application, you need to add your API on top of already existing Android API, and in the hull, to implement the hull, you have to just create a please refer the AOSP documentation for the implementation of hull, for example. And here application is here, and my interface helper class, for example, here, and AIDL is here, and here that my interface system services, for example, my class service, for example, here in HIDL, within HIDL, and my interface helper class is within AIDL, and in the user space my interface hull is here, and kernel space dedicated hardware is here, and as a legend, these are the third party and ST, and this is a community in black color community and ST add-ons, and this is hardware. As an example, we can consider sensor open module device function, and it's a convenient API for opening and closing a device. As another example, we can consider about sensors open function here, and if it return non-zero value, here you can see the error handling code here. And there are other HALs. In this architectural diagram you can see some other HALs, graphics, audio, camera, Bluetooth, GPS, audio, RIL, and Wi-Fi, and etc. For example, we can consider GPS. Here now we are considering Linux kernel. The foundation of the Android platform is the Linux kernel. For example, the Android Runtime ART relies on the Linux kernel for underlying functionalities such as threading and low-level memory management. In this diagram you can see the Linux kernel in the center also. Now we are considering drivers. The Java C tool read class and reason of choosing Linux kernel for Android OS is that Linux is really good at the basic operations such as networking, vast array of device drivers which take the pain out of interfacing to peripheral hardware. Here is the stack overview of applications over Android framework. Here applications similarly, and you can see here drivers, audio, bind, IPC, Bluetooth, camera, display, keypad, shared memory, USB, Wi-Fi, etc. USB and Wi-Fi. Here you can see audio driver. An audio driver is a type of computer file used by a computer's operating system OS to recognize and properly interact with an audio device. It usually refers to a driver used for a sound cards within a computer, but can also be used in reference to a drivers necessary for especially complex sound systems or audio input devices as well. An audio driver may come with a piece of audio hardware or may be downloaded or updated through the internet. Here you can see framework diagram of an audio system. The functional interfaces provided to the applications are audio track and audio record, which are functional interfaces of playback and recording respectively. These two functional interfaces call audio flinger through audio system. This is audio system and audio flinger. The audio flinger controls the buffers and playback. And audio flinger also managed by audio system. The management strategy comes from audio policy. Audio policy decided which type of audio and audio routing is music or phone calls, what kind of playback device music can turn on, whether to turn on the speaker or turn on the receiver, whether the phone is coming or not. Audio strategies such as music off, so on, including MKT's audio parameters will also be loaded here. And here you can see audio tracks and its audio record, and it's connected to audio system, audio flinger, and it's moved to audio mixer, audio resampler, and this one is connected to the audio system, audio policy service, and interact with audio policy interface, audio policy manager. Here it's communicate with in the HAL layer. Audio hardware interface is connected with the audio interface, and audio flinger is connected with the audio stream out, and audio flinger is connected to the audio stream in, and these three interfaces are connecting with the audio driver here in the kernel. As an example, we can consider this struct v412 underscore audio. This struct v412 underscore audio in video dev2.h header file. In this example, we can consider IOCTL function. This is information about the current audio input. IOCTL int video c underscore g underscore audio struct v412 underscore audio. Pointer to query the current audio input application, zero out the reserved array of a struct v412 underscore audio and call the video c underscore g underscore audio IOCTL with a pointer to this structure. Drivers fill the rest of the structure or return EIN val error code when the device has no audio input or none of which combine with the current video input. As a general error code example, we can we can consider EA gain, or also known as E-wood block. The IOCTL can't be handled because the device is in state where it can't perform it. This could happen, for example, in case where device is sleeping and IOCTL is performed to query statistics. It is also returned when the IOCTL would need to wait for an event, but the device has opened in non-blocking mode. function for this example is ioctl int video c underscore g underscore audio struct v 412 underscore audio pointer. Now we are considering binder IPC, a special driver for Android with a separate device node to achieve the function of inter-process communication. Here we can see a Android binder framework. In the Linux OS there are several techniques to achieve IPC inter-process communication, like files, sockets, signals, pipes, message queues, metaphors, shared memory, etc. However, Android's modified Linux kernel comes with a binder framework which enable RPC, remote procedure call mechanism, between client and server processes, where client process can execute remote methods in server processes as if they were executed locally. So data can be passed to the remote method calls and results can be returned to the client calling thread. It appears as if the thread from the client process jump into another remote process and start executing. They are known as thread migration. Basically, IPC inter-process communication is a framework for the exchange of signals and data across multiple processes, used for message passing, synchronization, shared memory, and remote procedure calls. Enables information sharing, computational speed up, modularity, convenience, privilege separation, data isolation, stability. Each process has its own sandbox address space, typically running under a unique system ID. In binder, the term is used ambiguously. The binder refers to overall binder architecture, whereas a binder refers to a particular implementation of binder interface. Here you can see user and space here, and client can connect with the binder driver here. It's through Open and ioctl, and in the Android application, client and server can connect through IPC, and server can connect to the binder driver in the Open and ioctl, and service manager can connect through the binder through ioctl. And this is kernel space. This is the binder driver, and it's in the /divide/binder in the Android platform. As an example, we can consider IPC underscore add ID function, an entry new to the IPC IDS IDR. The permission object is initialized and the first free entry is set up and the ID assigned is returned. The new entry is returned in a locked state. On success, on failure, the entry is not locked and the negative error code is returned. As an error example, on failure the entry is not locked and a negative error code is returned in this IPC underscore add ID function here. Now we are considering display driver. The display driver on Linux updates contents onto the display. Here you can see the architecture of Android graphics. Android consists of a user level native layer and Linux kernel. The native layer includes HAL and Surface Flinger service. Virtualizing graphics architecture of Android mobile platform in KVM and ARM environment. In Android graphic architecture stack, in which the process called Surface Flinger plays a central role. Surface Flinger issues allocation request of memory buffers to the ION device driver. in the underlying Linux kernel via graphic HAL hardware adaptation layer. After the memory buffer is allocated, Surface Flinger issues OpenGL commands on the memory buffer to build graphics image and then composes multiple buffers into a single buffer with the help of HV composer HAL. Then Surface Flinger sends the composed buffer to the display device. Finally, the content in the composed buffer appear on the physical display device such as an LCD. ION is an integrated memory allocator for graphics buffer memory used by I/O devices such as the GPU, display controller and camera. Before Android 4.0, each vendor provided its own specific memory allocators and interfaces, so compatibility was an open issue across different vendors Android devices. In order to solve this compatibility issue, ION was introduced with Android 4.0. Since then, Surface Flinger has been able to allocate buffers using ION. Fence is a synchronization framework that facilitates the management of graphics buffers accessed by multiple processors. Memory buffers are concurrently accessed to fill up with display contents by multiple processors called producers and consumers. GPU, the embedded graphics library EGL and OpenGL ES have been adapted to support 2D and 3D graphics acceleration in Android mobile devices. EGL is an interface worked with OpenGL ES that is required to manage graphics contents, window system, surface and buffer binding, and rendering synchronization. Also, the Graphics GL ES API is used to render the compromised surfaces by application Surface Flinger. Vendor provided OpenGL libraries send several file operations to the GPU device driver. VSync and display. A VSync is a synchronization signal generated by a display device as a notification that the contents of a buffer are completely displayed and buffer is now free. So VSync is very important to smooth animation. VSync first appeared in Android Belgium. Typically, a display device sends the VSync interrupts to the display device driver periodically at the display refresh rate interval. Here you can see the user and this application in Surface Flinger is there in external library. In the external library you can see OpenGL ES and EGL. Here HL library, hardware composer and Gralloc. And in this is Linux kernel, you can see system, VSync and display driver and fence and GPU driver and ION driver and hardware, display device, frame buffer and GPU and main memory. Here as an example we can see MIPI underscore DSI underscore DCL underscore set underscore display underscore brightness struct MIPI underscore DSI device pointer and U16 function sets the brightness value of the display. As an error example, a negative error code on failure in function MIPI underscore DSI underscore DCL DCS underscore set underscore display underscore brightness function here. Now we are considering keyboard. A keyboard driver is a software which allows communication between your keyboard and your PC or laptop basically. Here you can see a Android input subsystem below this is an architecture diagram for basic working model of Android input subsystem. We will explain each of these blocks and how they are intervened to achieve the user input interface user cases. As a input pipeline explanation, at the bottom level, the physical input hardware device indicates that the state of the device has changed by generating an electronic signal such as a button or touch. The device firmware then encodes these signals and report them to the system via the USB HID or via the I2C bus. After receiving this signal, the Linux kernel decodes it through the device driver. Linux kernel provides drivers for many standard peripherals, especially the standard HID protocol. Linux input device driver is responsible for converting device specific signals to standard input events formats via the Linux input protocol. Linux input protocol defines a standard set of event types in the /include/linux/input.h header file of the code. Android Event Hub then reads the input device event by opening the event device driver associated with the device. Android input reader then passes the input events based on the device class and the Android input event stream. In this process, Linux protocol event code will be converted to Android event code by input device configuration file *.idc, keyboard layout file *.kl, and various mapping tables *.ckm. Finally, the input reader sends the input to the event to the input dispatcher, which then sends the input to the appropriate window using the view root implementation. So this is the flow, and here you can see input reader thread and input dispatcher thread here, and this input mapper here. In between communication. As an example, we can consider input _report _key function here. Call to the input system. There is no need to check whether the interrupt routine is reporting to the same value events. Press for example to the input system, because the input _report _ functions check that themselves. As an example, we can consider input as an error example. We can consider return value of input _register _device function here. If it is the value is greater than 0, then you can see the error handling code here, and this function registers a device with the input core. The device must be allocated with the input allocate device and its all its capabilities set up before registering. If the function fails, the device must be freed with input _free _device. Once the device has been successfully registered, it can be unregistered with input _unregister _device. Input _ free _device should not be called in this case. The relevant function is input _register _device struck input _device pointer. Now we are considering Bluetooth driver. A Bluetooth driver is a software program that allows your operating system to communicate with the Bluetooth device and conversely. Android Bluetooth software stack. Here you can see the Android Bluetooth software stack. Bluetooth driver, hardware dependent. Device driver providing access to the Bluetooth hardware device to HCL sockets of the Bluetooth family. AF underscore Bluetooth / BT proto underscore HCL comma HCIO interface. And this is Bluetooth HAL Bluetooth Android native component implementing the Android Bluetooth HAL hardware interface definition language on top of the kernel Bluetooth subsystem used by the Bluetooth stack. Bluetooth Fluoride stack libbluetooth.so native Bluetooth stack built as a shared library. The stack integrates its own implementation of all required profiles and transport protocols by using the HCL support of the host system through the HAL offered by the Bluetooth HAL to communicate with the Bluetooth device. Bluetooth system service. Bluetooth application providing managed level Bluetooth profiles and services. The application uses JNI to load and run the Fluoride stack and exposes itself to the rest of the system through the system service implementing the Bluetooth AIDL Android interface definition language. And framework Bluetooth API. And Android.Bluetooth API is providing application with framework level access to the Bluetooth subsystem. Internally, the code uses client-side Bluetooth AIDL to interact with Bluetooth system service exposed by the Bluetooth application through the binder IPC mechanism. And here you can see in kernel space BT Bluetooth driver is here and HCL is here, but this communication is going through, and AF Bluetooth sockets here they are in this user space, and BT hull is here and libct.vendor is there, and Fluoride core is here, and in JNI level in the JNI and Bluetooth system services are here, audio, TTLE, RFCOM, serial and file e-exchange, headset, and in AIDL is there, and Bluetooth helper classes are here, and Android.Bluetooth and application settings are here. In legend you can see third party SD, community SD add-on and hardware here. As an example, we can consider HCI underscore UART underscore register underscore proto struct HCI underscore UART underscore proto pointer function. It's in HCI underscore UART header file. For example, for a error, we can consider UCI underscore register underscore HCI underscore UART underscore register underscore proto function, and you can see the error, and you can see the error handling code here in the else segment. and this function is in HCI_UART header file. Now we are considering camera. The camera's driver interact with the actual camera hardware and your implementation of HAL. The camera and driver must support YV12 and NV21 image formats to provide support for previewing the camera image on the display and video recording. Camera, you can see the camera architecture here. The bottom layer is the camera driver, which is strongly related to the hardware. The top layer of camera driver is operation driven camera HAL layer, which is also the core code of the camera's manufacturer's camera. The manufacturer encapsulates its own code well without observing the open source condition. The camera HAL layer is also the focus of modification and optimization which run the process of camera provider. The camera service is a bridge between camera provider and the upper communication, just as an intermediate layer. Camera framework is a well-known call interface for developers. So this is the basic camera architecture here. As an example, we can consider OV774 set_white_ balance function. In the source file for this function is media/i2c/OV7740.c. As an error example, we can consider the return value of OV774 set_white_ balance function and returns null. The reg map for device is not present. In shared, now we are moving into a shared memory. The shared memory driver pre-allocates the required shared memory using DMA APIs at boot up and then allows the region of memory to be shared with the peripheral processors using kernel QMI service. The allocated memory would be designated as uncached. Here we can see the application framework. At the bottom is the kernel layer, which is the anonymous shared memory driver we will introduce, and it creates a device file of /device/ASH mem at startup. The upper CUTIL's library accesses the driver through the file access operation, open and IOCTL. In addition, CUTILs mainly provide three functions: ASH mem _create _region and ASH mem _pin _region, ASM pin ASH mem _pin unpin _region. Finally, there's an application layer encapsulation. What we actually use is the interface provided by this layer. Android uses a file descriptor to represent a block of marked shared memory and passes this file descriptor through the binder_type_ft command for interprocess communication. And here you can see C++ interface memory base / memory base memory heap base and Java interface memory file. So here kernel and this is runtime libraries, and this is the application framework. As an example, we can consider ashmem.c file, ashmem.h file, and in UAPI /ashmem.h file. This anonymous shared memory driver is defined in kernel, and three files may be involved in the latest 3.18 kernel. And as another example, we can consider struct ashmem_area, struct ashmem_range, and struct ashmem_pin. There are three important data structures in the driver. As another example, we can consider ashmem_open, struct inode pointer, and struct file pointer function. It's open and anonymous shared memory structure. As an example error code, we can consider eno mem cannot allocate memory. The system cannot allocate more virtual memory because its capacity is full. In the function ashmem_open in the source file ashmem.c. Now we are focusing on USB driver. A USB driver is a file that allows a hardware device to communicate with the operating system of a computer. This is the Android USB device framework architecture. From this architectural diagram, you can infer that the composite infrastructure is a part of the kernel, and most of the USB device functions are implemented as class drivers within Android Linux kernel. There are exceptions like ADB and MTP, which are implemented in both sides, that is the kernel and the user space. In such cases, kernel driver implements just the transport part of USB, guaranteeing delivery of data. The Android frameworks perform the functional management, implementing class level protocol, which other chapters of this book other parts of this are there also. And here you can see USB control driver is here, then it moved to USB gadget driver and USB composite driver. Design Android kernel space, and this is Android user space. Is connected with the USB service and USB function. This is JNI and other infra here, and this is Java USB service, and it's going up to Android USB API, android.hardware.usb. As an example, we can consider struct USB_driver. This identifies USB interface driver to USB core. As another example, we can consider USB_submit_URB function. This submits a transfer request and transfers control of the URB, describing that request to the USB subsystem. Request completion will be indicated later asynchronously by calling the completion handler. Three types of completion are success, error, and unlink, a software induced fault also called request cancellation. As an error example, we can consider the return value of USB underscore submit underscore URB function here. So if 0 on successful submissions and a negative error number otherwise, here you can see the error handling code here. Now we are considering Wi-Fi, a software Wi-Fi driver, a software that is needed by the computer or laptop to communicate with Wi-Fi adapter or other Wi-Fi devices. Here you can see Android Wi-Fi architecture. Application framework code for Wi-Fi manager, Wi-Fi monitor, Wi-Fi configuration are in base/Wi-Fi/Java/Android/net/Wi-Fi folder. JNI code written in Android_net_Wi-Fi_Wi-Fi.cpp located in frameworks/base/core/GNI folder, which communicate with HAL layer. HAL layer's code is written in Wi-Fi.c hardware/lib hardware/legacy/Wi-Fi/ code in Wi-Fi.c file communicate with WPA_ supplicant over control interface. As shown in the architecture, applies to the wireless drivers, which uses wireless extension to communicate with the driver, with the implementation of as shown in the application architecture applies to the wireless drivers, which uses the wireless extension to communicate with the driver. So here you can see the kernel space, and you see the wireless driver, and here TCP IP, and here VEXT, and this is a native process, and system core system4/core libnet_util.so, and here hardware /Wi-Fi C and libwpa client.so, and this is DHC PCD and SQLite key store and WPA_supplicant here. On top of that, these SO files are there, and this is Java framework, and you can see Wi-Fi native JNI is here, and Wi-Fi stack tracker, and here Wi-Fi monitor and Wi-Fi watchdog service here, and here Wi-Fi service, and on top Wi-Fi manager is here. This is the Android full Wi-Fi architecture. As an example, we can consider here Wi-Fi_platform_get_IRQ_number function. Get the customer specific OOB IRQ parameters, that is IRQ number as IRQ type. The relevant header file for this function is /command plus /bzm hdhd /3.10 /drivers /net /wireless /bzm dhd /dhd_linux.h header file. As an error example, we can get the return. We can consider return value of Wi-Fi_platform_get_IRQ_number function, and you can see the error handling code here. If the return value is less than 0. Now we consider power management. Android supports its own power management on top of standard Linux power management, designed with the premise that the CPU shouldn't consume power if no applications or services require power. Android requires that applications and services require CPU resources with wake locks through the Android application framework, and native Linux libraries. If there are no active wake locks, Android will shut down the CPU. Here you can see Android Android power management architecture. Solid elements represent Android blocks, and dash elements represent partner specific blocks here. Here application A, application B, application C is there, and wake locks are used by application and services to represent CPU resources. A locked wake lock, depending on its type, prevents the system from entering, suspend, or other low power states. So here there are wake locks and acquire and released, and it's linked with the this is applications, and this is application framework, and it's going through the power manager, android.os.power manager, and it's moved to power and android.os.power, and it's go to power manage service, android.server.power manager service, and it's moved through JNI. It's go to libraries, usage space, and this is power and lib/hardware/power C. It moves to power manage Android power management in Linux kernel area, and this again is moved to this is /drivers/android/power.c, and this is Linux power management. And here this is partner specific blocks. You can see Linux drivers and Linux Android underscore register underscore suspend and this under function, and Android underscore register early resume functions go through the Linux power management from there, and it's connect with the Linux power management here also for the power C function. And here core libraries might connect to power manager here. As an example, we can consider struct dev underscore pm underscore ps, a device pm callbacks. There are many fields here, and this struct. As another example, we can consider pm underscore wake up underscore event function. PM underscore wake up underscore event notify the PM core of a wake up event. Wake up resource object associated with the event source, anticipated event processing time in millisecond. Notify the PM core of a wake up event whose source is that will take approximately millisecond to be processed by the kernel. If it is not active, activate it. If it is non-zero, set up the timer to execute PM underscore wake up underscore timer underscore fn in future. As an error example, notify PM core of a wake up event whose source is that will take approximately millisecond to be processed by the kernel. If it is not active, activate it. If it is non-zero, set up the timer to execute PM underscore wake up underscore timer underscore fn in future. This is a guideline and in the function PM underscore wake up underscore event basically. This is the end of the presentation of Android architecture. I am Stefan Silva, and thank you very much for watching the full architectural video.